Today we're diving into a paper that explores how to enhance large language models, LLMs, with the ability to understand and reason about graph data. The paper, GraphInstruct, Empowering Large Language Models with Graph Understanding and Reasoning Capability, proposes a new benchmark in training methods to achieve this. Let's start with the benchmark. What is GraphInstruct and what makes it unique?
GraphInstruct is a benchmark specifically designed to evaluate and improve LLM's capabilities in handling graph-structured data. It's unique because it goes beyond simply testing LLMs on graph data. It provides a comprehensive set of 21 classical graph reasoning tasks covering a wide range of complexities, from basic tasks like finding node degrees to more challenging ones like calculating maximum flow or finding minimum spanning trees.
That's a diverse set of tasks. How does GraphInstruct ensure that the LLMs are truly understanding the graph data rather than just memorizing patterns?
GraphInstruct incorporates several features to address this. First, it generates graphs with diverse structures and sizes, including random, small world, and scale-free networks. This forces the LLMs to generalize their understanding beyond specific graph types. Second, it offers different ways to describe the graph, such as edge lists, adjacency tables, and natural language descriptions. This tests the LLM's ability to adapt to different input formats.
So the benchmark is designed to be challenging. What about the training methods? How does the paper propose to train LLMs to perform well on GraphInstruct?
The paper proposes two main training approaches. The first, called GraphLM, uses instruction tuning on the GraphInstruct benchmark. This involves fine-tuning a pre-trained LLM on the tasks and answers provided in the benchmark. The second approach, GraphLM+, goes a step further by incorporating intermediate reasoning steps into the training process.
That's interesting. Why are intermediate reasoning steps important for improving graph reasoning capabilities?
Intermediate reasoning steps provide the LLM with a more detailed understanding of how to solve a graph problem. Instead of just learning to associate a graph with a final answer, the LLM learns to break down the problem into smaller steps and reason about the relationships between nodes and edges.
So GraphLM Plus is essentially teaching the LLM to think like a graph theorist. How does the paper address the challenge of training on these intermediate steps?
The paper introduces a label-masked training strategy. This strategy involves selectively masking out certain words in the intermediate steps during training. The goal is to focus the LLM's attention on the most important information, such as node IDs, while filtering out redundant or less informative words.
That's a clever approach to dealing with the verbosity of intermediate steps. What are the key findings of the paper?
The paper demonstrates that both GraphLM and GraphLM Plus significantly outperform baseline LLMs on a variety of graph reasoning tasks. GraphLM shows improved performance on tasks it was trained on, while GraphLM Plus exhibits even better performance, especially on tasks requiring reasoning steps.
So the paper shows that LLMs can be trained to understand and reason about graph data. What are the limitations of the current work?
The paper acknowledges that the models still struggle with some complex graph reasoning tasks and out-of-domain tasks. This suggests that more training data and potentially more powerful baseline models are needed to further improve performance.
That makes sense. What are some potential future directions for this research?
One direction is to explore the use of more advanced graph neural networks, GNNs, in conjunction with LLMs. GNNs are specifically designed to process graph data and could potentially provide LLMs with a more robust understanding of graph structure.
That's a promising avenue. What about the application of this research to real-world problems?
The paper focuses on abstract graph reasoning tasks, but the potential applications are vast. For example, LLMs with graph reasoning capabilities could be used to analyze social networks, predict traffic patterns in urban environments, or even assist in drug discovery by understanding the interactions between molecules.
That's exciting. What are some ethical considerations related to this research?
As with any powerful AI technology, it's important to consider the potential for bias and misuse. For example, LLMs trained on graph data could be used to reinforce existing social biases or to create discriminatory algorithms. It's crucial to develop ethical guidelines and safeguards to ensure that these technologies are used responsibly.
That's a critical point. What are some potential benefits of this research?
LLMs with graph reasoning capabilities could revolutionize how we analyze and understand complex systems. They could lead to breakthroughs in fields like medicine, finance, and social science. Furthermore, they could empower individuals to make more informed decisions by providing them with insights from complex data.
So this research has the potential to both benefit and challenge society. What are some of the key takeaways from this paper?
The paper demonstrates that LLMs can be trained to understand and reason about graph data. It introduces a new benchmark, GraphInstruct, and two training methods, GraphLM and GraphLM+, which show promising results. The research highlights the importance of incorporating intermediate reasoning steps into the training process to improve LLM performance on graph-related tasks.
This was a fascinating discussion on the technical aspects of this paper. Thank you for your insights.